All right, welcome to our next CU Prime talk. So my name is Tyler. This is Reuben. He's going to be the speaker for today. If you don't know what CU Prime is, we are a group, student org. We can go to the next slide. It's dedicated to increasing diversity and equity and inclusion in the physics department here in CU Boulder. There we go. So one thing that we've started to do is to give a talk each year after the Physics Nobel Prize comes out. And so that is what today is all about. So we're going to hear about what the Nobel Prize was awarded for, and maybe how that work relates to some work that was done at CU. And also we'll hear about Reuben's life as a grad student. So feel free if you're in the room to grab more pizza. I already announced it, but be sure to sign in if you haven't already. So we have a good track of numbers of who is here and how much pizza we should order in the future. And as always, if you have any questions for the speaker, feel free to interrupt any things that you are wondering or curious about, and we'll have times of discussion throughout the talk. So let's give it up for Reuben.
So, cool. So, hi, everybody. I'm here to talk about the 2022 Physics Nobel Prize today. And that's titled Tinkering with Bell Pairs, and we get to kind of why it's titled this way, of course. But first, before we begin, just to kind of tell you a little bit about my pseudorandom walk through life and how I kind of got to this point and where I am. So I grew up actually in Singapore, which is a really small island country city place. And I think if you have any kind of handheld globe, you probably won't be able to spot the country on the map because it's so small. But you know, it's kind of a nice place with nice things and nice people, and it's a tropical island. And I did my undergraduate there, but actually I did my undergraduate in engineering. So I did it in the university called the Singapore University of Technology and Design. So I started there, and I did engineering. But it was during one of these summer research programs that I first encountered physics research. So I did research with a theoretical physicist, and it was my first introduction to theoretical quantum physics, and it was really exciting for me. And so I decided, well, I don't want to do engineering and, you know, troubleshoot circuits for the rest of my life. I want to explore the secrets of the universe. And so I switched over and I applied to a program in physics for a year. And so I did a year of physics at MIT. And there I kind of had, you know, a whole bunch of physics. Basically, I just overloaded a whole bunch of courses to get up to speed with physics. And it's probably one of the most intense periods of my academic life. But that allowed me to then apply to grad school in physics. So I'm now doing a PhD program in physics right here at JILA. So that's how it brought me here. And JILA is great. And so JILA is part of an institute at CU Boulder, which is the building adjacent. And I'm always pointing the wrong that way. Thank you. Yeah, which is another research institute for physics. So that's where I currently am at. So you can see my path has kind of been all over the place. I mean, starting with engineering and then gradually moving to physics. But I like to share a quote with one of my professors with you. And so this is Professor Jesse Thaler, and who was my first lecturer at my first class at MIT. And he said these words in the first class: there are as many ways to be a successful physicist as there are successful physicists. So I think these are words that I've definitely helped, you know, close to me, and I hope they kind of inspire you no matter where you are in your journey in physics. So hope that encourages you. All right, but let's get into the meat and potatoes of this talk. So first of all, congratulations to the 3 winners of the Physics Nobel Prize 2022. And these are Alain Aspect, John Clauser, and Anton Zeilinger for their fundamental experiments on entangled photons, Bell's inequality, which is what we'll more or less get into today, and quantum information science. So these are really pioneering and trailblazing works in quantum information science. That's been really cool. But yeah, so we'll talk more about Bell's inequality, which is really kind of a simple idea at the face of it, but it really has really profound implications for the theory of quantum mechanics, which is really cool. And hopefully I can convey that to you today. All right, so let's start with a brief overview of quantum mechanics in general. So quantum, what does quantum mean? Why is it called quantum mechanics in the first place? Well, the word quantum comes from the Latin word quantus, which means a small amount or some amount of some phenomena. So some discrete packet that you can associate to some physical phenomena that you're talking about. And so this motivates the study of quantum mechanics, or quantum mechanics was motivated to be named this way because in our physical world, when we have confined systems, there's some properties of the systems that tend to be quantized. And so this notion of quantization is what alluded to quantum mechanics. And so even in classical physics, so classical, when I use the word classical, I just mean anything that's not quantum. There's this notion of quantization that happens too. And I'm going to show a little video. Hopefully it plays over here. Let's try to get theater mode. It's not going there. Okay, fine. But so over here, you can see a plate with sand on it. And all that's happening is the plate is vibrating via a speaker at the bottom of it. So you're playing some notes at some specific frequency. So you can see the frequency over here. And depending on that frequency, the system changes and has some wave modes. These are called normal modes of the system, which I like to think about it as these fundamental states of your system. So you can characterize your entire system by thinking about decomposition of the system into these normal modes, which are these fundamental ideas and fundamental states of that particular system. And so this arises because you have a finite size plate. So this is not an infinitely large plate. And you get this effect of quantization in your classical system. So I'm using quotes here because it's not an actual quantum system, but it draws a nice analogy between what I'm going to talk about today. All right, so going back to my slides. Right, so even in classical systems, you get this kind of notion of fundamental states of your system. And what happens in quantum systems is that not only are there quantization effects when you have finite size systems, but also there are certain properties of your quantum system that are innately quantized. So there are certain properties, like one of the examples here is spin, which I think Jacob has talked about in a previous CU Prime talk, really nice talk. And so these things can kind of be innately quantized and innately discrete in nature. So some of these ideas come about when you look at, angular momentum, which is, when you have a particle orbiting another particle in some system, like the Earth orbiting the sun. And in a quantum system, the analogous system becomes quantized in the sense that the angular momentum can only take discrete values of L over here. All right, so let's ground this more into a more relevant example for what we'll be talking about today. And that's quantization of polarized light. And so I have a little GIF over here. Hopefully it plays. Is it playing? Is it not playing? Oh, everything is lagging on the screen. It's playing on my screen. Coming through, Tyler? Oh, there it is. Yay. Okay. So as you can see, polarization is not something that we're unfamiliar with. So if you have any pair of sunglasses and you rotate those sunglasses at a computer screen, because the light that's coming out from your computer screen is polarized, your sunglasses are basically a form of polarizer, which will prevent a particular polarization of light from passing through your sunglasses. And this is how your sunglasses protects your eyes from sunlight. And I'm going to stop this. This is a little distracting. Oh, okay. But so this idea that you can have polarized light, well, usually you describe light in terms of classical electromagnetic fields. And so these classical electromagnetic fields are kind of this notion of waves that are coming in, and that vary over space and time. But there's this wave notion of classical electromagnetic fields that if you pass through a polarizer, because of the ways those fields interact, we can get polarization effects. But when you look at the quantum context, so light can also be described quantum mechanically, which means that you can have quantized packets of light. So these quantized packets of light are called photons, and they are, come in as a wave particle duality description of our universe. And many other things can be described in this way. But so photons, you can think of them as both having wave properties and particle-like properties. And so you can quantize particles of light as photons. And we'll get back to this idea in just a second. But let me take a step back and zoom out a little bit more and kind of talk to you in a general sense about quantum mechanics. And I'll try to summarize most of quantum mechanics in a slide. Hopefully this will do. But just to tease out some particular key aspects of quantum mechanics that we'll need for the rest of the talk. All right, so in general, this is just for all physics in general, right? You can categorize your theories of physics into two broad pillars that will support your theories of physics. And the first thing is going to be the dynamical variables of your theory. So these are things that characterize the state of your system and things that change in time, right? So for instance, you can have like a classical mechanics model or some classical mechanical system, like a system of pulleys or balls on ramps and whatever fun physics that you have to do in your first year here. But they can be characterized by the position and the momentum of those classical objects, right? So x and p are the position and the momentum of those objects. If you look at a general Maxwell's theory of electromagnetism, you can quantify these things by electric and magnetic fields. And as for quantum mechanics, the state variable of the system is really the quantum state, or the wave function that some people call it. And it's characterized by this letter over psi. And this angle bracket with a straight line over here, we refer to that as a ket. And I think Jacob has also mentioned this in his previous talk. But we can just think of it as a generalized way of labeling states. So whatever you put between these angle bracket and the line is going to tell you about some characteristic of your state. And you'll kind of get back to this notion of using a generalized labeling method. The other thing that people call this ket, or KET is what they call it, is also called a vector. And why it's called a vector is because you can imagine this state as some arrow pointing in some space. And that'll be very useful to think about because we'll talk about these arrows later as they vary in space. And so any kind of quantum state, you can just imagine as some vector pointing in some space, right? So vector is just an arrow that points in some space. Cool. So the other important part of a physical theory then is the equations of motion. So these are the instructions that tell you how the dynamical variables of your system change in time. And so for instance, some famous dynamical equations of motion are F equals to ma. So if you apply a force to your system, the position of that particle is going to accelerate by ma, by force ma, and that's going to tell you how your position changes in time. So that's one equation of motion. And for quantum mechanics, of course, the famed equation of motion is the Schrodinger equation of motion, which tells you how your psi changes in time, which is, I think it's it. So how psi changes in time, which is, this time derivative over here that you have, and then h, that operator over there, or this object h, is going to kind of tell you about the energy of the system. So maybe in a general sense, it's not too important for this talk, but for those of you who know those words, that's useful. Cool. So some peculiar aspects of a quantum theory in particular, so not just a general theory of physics, but particularly a quantum theory, is that there's this aspect of loss of determinism. So I think many of you, even if you have no background in physics, you've gone to like a general physics, kind of science communication talk. They'll talk about, oh, there's these probabilistic things that happen in physics, in quantum physics. And this is because of the notion of loss of determinism. And I'll elaborate on that in just a second. But so two other key aspects of quantum theories are superposition and entanglement. And entanglement, and these two things are, of course, very interrelated, but entanglement really is kind of the crux of what we'll be getting into today. And so this is, of course, something I'll elaborate in more as well. So let's get first into loss of determinism. So, okay, so quantum mechanics, there are actually two parts to quantum mechanics, which are actually quite distinct. And it's quite interesting to think about, because there's one part where you say you have this state in your, in your vector space, so this vector that points in some space that you have, and that evolves in time via the Schrodinger equation. So you can imagine as that vector moving and pointing in different directions in some space that you're in. And that's deterministic. And so what that means, if you tell me everything there is to know about psi, so if I give you a psi at some specific instance of time, and you can fully characterize that state, so that arrow, you can tell me all of the components of the arrow, I can tell you exactly how that state is going to evolve in time. And so this is fully deterministic and not too different from your usual classical theories. But where the probabilistic aspects come into play is when you do a measurement on the system. And this is where things start to get really weird, because in quantum mechanics, quantum states are just a probabilistic description of your system. And what ends up happening is that if you measure a particular quantity in that physical system, that state that's moving around in your space is going to collapse to this one of these fundamental states in your system. So it's kind of analogous to this idea where you had these normal modes earlier with this, stand on a plate. And so that characterizes kind of the coordinates of your space. And so if you measure this arrow that's moving around in your space, it's going to collapse to one of those states. And it's going to collapse via this probability that is actually just the shadow of this arrow onto this arrow. So it's the overlap of the two arrows that's going to tell you the probability of measuring that particular quantity. All right, so for an example, earlier we had this, polarization of light. And really, actually, there are two fundamental ways you can polarize a photon of light, right? Which is, and I always get confused, vertically polarized and horizontally polarized directions. So those directions form your coordinates of your space, and any other polarization can be made up of a combination of these two arrows pointing in that space, right? So you can sum up two arrows, and then you can make any other direction in that space. And so any arbitrary state of polarization can be described by these two fundamental states. But if you're not on those two axes, so you point in some arbitrary other direction, that is what you call a superposition of the two fundamental states of your system, right? So this is where superposition arises. You can be described by both of your fundamental states at the same time. That's a superposition. And of course, you can see the blue arrow and the red arrow, where they overlap, or the shadow of the blue arrow onto the red arrow is the probability of you measuring the up state or the vertically polarized state or the horizontally polarized state. All right, cool. And I have a little plus over here. And what this plus means is that your actual polarization, you can be parallel or anti-parallel to a polarization. So parallel is plus, anti-parallel is minus. So that will be useful to keep in mind for the later part of the talk. All right, cool. Now, so we kind of get this idea of, superposition as this arrow pointing some space, and it can be decomposed into these fundamental states of your system. But what really is entanglement? So entanglement only arises between two or more quantum particles. So if you have a system of two or more quantum particles, what can end up happening is that these particles can develop a special kind of correlation between them, and they're called quantum correlated or entangled in a particular way. And this arises only very specifically in very specific scenarios. And I'm going to talk about how you might want to think about these things. So imagine you have two particles, A and B. And so early on, we had these kets, right? These vectors. And now this circle with an X or with a cross in the middle of it is just a way for you to put these two particles into a comprehensive description of that entire system. So it's telling you, I have two particles in that system. I want to describe the larger system. I put this O with an X in the middle to just combine these two things. And for ease of notation, so because earlier we said that this ket is just a way of labeling things, we can just truncate that notation and say, well, we all know we're going to be talking about two particles in the system. I'm just going to put them into the same ket and call that one vector, but we know it's talking about two particles. So that's a convenient way to represent things. So here's an example of a system of two particles, but that's not entangled, right? So this is very complicated. So you have all these different states, and it's a superposition of two particle states, right? So if you have two photons passing through a polarizer, they can be, upper polarized or up horizontal polarized, or all these different combinations. But if you can factorize the state into two different states, or in other words, if you can apply two individual rotations in the state space individually to the two different photons, then they're not entangled, right? But conversely, if you can't do that, you get them to be entangled, of course. So if you have to do a global operation, what we call a global operation, which is an operation simultaneously on both photons, in order to get them to be correlated in this special way, and you cannot factorize the state into two separate photon states, then we call that state entangled. So this is kind of the notion of entanglement. There's no way of separating the two subsystems back apart from each other. They're kind of intrinsically correlated to one another. Cool. All right, so let's get some audience participation right now. So I'm going to have a little question. All right, so I have four states over here. Just to make sure that you guys fully understand what entanglement really is, can you tell me which one of these states is entangled? And so maybe discuss this with your neighbor. Okay, so who can tell me which state is entangled? Three? Any other answers other than three? No? Three? All unanimous three? That's right, it's three. Cool. Because the first state is just one particle, so you can't have entanglement between one particle and itself. And the other two states are factorizable, so they're not entangled, so only state three is great. All right, cool. Everybody is an expert now at entanglement, so we can move on. All right, so let's get into some of the work that the Nobel Prize was getting at right now. So this is Bell versus EPR, and I'm going to say who Bell is and who EPR are, and we'll understand this better. All right. So in 1935, Einstein, Podolsky, and Rosen, two well-renowned physicists at the time, and even right now, claimed that quantum mechanics as a theory was incomplete because they believe it defied what they called as local realism. And so local realism is an idea or a concept that can be, of course, split into parts because it's two words. So realism is the notion that objects in our physical world are real. And what that means is this nice analogy that people always talk about. If there's a tree somewhere far away in some forest and it falls, but nobody's there to observe it falling, did it really fall? Right? It's kind of a philosophical question that people like to raise up. And so realism says that, yes, there was a tree, it fell, even if there was nobody observing the tree falling. So that's the notion of realism. And locality, so local of there means that physical phenomena can only be affected by their immediate surroundings. And so, of course, Einstein was a big proponent of this because he came up with his All right, so back to these amazing people and scientists. So yeah, we have realism and locality, which are essential properties that these three scientists claim that there must be in the universe and there must be that describes a reality. So what they said in their paper back in 1935 was that either one of the two things, so either the description that quantum mechanics was giving of reality was not complete, or two entangled quantities cannot have simultaneous reality, meaning that you cannot have two entangled quantities that are both in existence at the same time, or have the same, have simultaneous reality, essentially. Right, and so with this, they said, well, quantum mechanics cannot be complete because either that or these two things. Cool, so, all right, so because of this conclusion that they're drawing, what they propose then is that quantum mechanics required a larger, broader sense of variables in the theory. And so what they call these things were hidden variables, meaning that there were some variables in the universe that experimentalists at that point of time couldn't measure, which is why it was hiding some information about the dynamics of that system. So if you can think about the entangled state, the one we just saw in the question that we had earlier, what Einstein, Podolsky, and Rosen said that such states are actually states of definite polarization. So if you have two photons again, and you measure their polarizations, instead of just having them as quantum entangled photons, what EPR would say is that actually, if you measure 100 of them, it's because secretly the universe is correlating them in some special way before you did the measurement, so that even before you did the measurement, the outcome of the measurement was going to be predetermined by their special correlation, which is in opposition to what a quantum state means. So quantum state means that before you do the measurement is in this probabilistic, weird kind of moving thing in some space. And only when you do the measurement will it project to one of these fundamental states, and then you get a measurement result. And so there's this funny, story that Bell likes to tell about one of his colleagues, Bertelmann, at the time, where he said, even in the classical world, there could be some really strange correlations because Bertelmann, his colleague, always wore different colored socks. So if he stepped in a room and he saw he was wearing a red colored sock, you know immediately that his other sock wouldn't be red. So this is kind of a strange correlation that you have in the classical world. But even so, Bell was a big proponent of saying, well, let's make sure that classical correlations are not the only thing in the universe, and quantum mechanics could actually be a valid theory of the point. All right, so EPR, we talk about these ensembles. So imagine you have 100 particles or 50 pairs of particles. What they would say is 50% of them would be correlated with vertical and horizontal polarization, and vice versa for the other pair of photons, right? And so here's another really quick question to maybe tease your brain a little bit. Can you and a friend conceive of a way of distinguishing 60 copies of an entangled state versus 60 classical correlated pairs? And again, go ahead and discuss with your neighbor really quick. Let's give you two minutes for this. All right, so in the interest of time, you're gonna ask if anybody got a vague notion of an answer. Anybody can tell me a way? Cool. Oh yeah, please go for it.
Yeah, we were thinking
that if it's a perfect like 50-50 split,
Mhm.
it's entangled, but a classical split could be more than 50%. So
So just like statistical noise.
Yeah.
So actually, even in a quantum system, because of statistics, you can still get, slightly different from 50-50. But yeah, great answer. Thank you. But so, okay, cool. Because so if you had gotten an answer, I would have told you, I wish you were born in 1964, because then maybe you'd be winning a Nobel Prize right now. Because that's what basically John Bell did in 1964. He came around and he said, well, let me think of a way I can distinguish quantum entangled states from classical ensembles. And his little trick, his nifty trick was actually to say, instead of measuring just along the two fundamental axis states, what I'm going to do instead is I'm going to add one more. So I'm going to measure in 3 different directions, and I'm going to call them axes A, B, and C. And so this is John Bell, when his incredible groundbreaking work in 1964, which was a theoretical thought experiment that he concocted to test this entangled state. All right, so here's the notion of what he was proposing. So like I said, instead of measuring along the two fundamental states that we have, which are vertically and horizontally polarized, I'm going to measure along 3 non-coincident directions, A, B, and C, with an equal angle theta between them, and then compare that to what I would expect from a classical ensemble of states. So, all right, so classical ensemble of states, there's 3 measurements now with 2 different particles. So that's a lot of possible different combinations, right? Because you have 2 things, you can measure them 3 ways, and they have to be correlated with one another. Meaning that if I measure one thing along one particular axis, the outcome of the other one has to be predetermined. If I was EPR and I was thinking these things would be classically correlated. All right, so here's a little table to give you a sense of how many combinations these things are. So you have to count all these possible, ensemble of states. So each of these brackets here corresponds to a possible outcome. Remember, the plus and minus means that you can either be parallel or anti-parallel to the particular axes. And so if I were to give you, or I were to ask you to measure, along one particular direction, and you have to tell me what the other particle is going to be measured as, then I need to tabulate all these possible different combinations. And so what ends up happening is if you count all these things, so all these numbers over here are if you had some arbitrary number of ensembles with a total number being the sum of all these n's, then the probability of each of these things occurring would be the number divided by the sum of the numbers over here, right? So that's just counting statistics. That's how you get probabilities. So this is how we get to Bell's inequality. So this is what it says. So any classical theory or any possible classical hidden variable theory that you can imagine will always satisfy this inequality. Meaning that if you had classically correlated photons, it must satisfy that if you measure along the A direction plus, if you measure a photon that's parallel to the A direction and a photon that's parallel to the C direction, so that the pairs of those plus B and C parallel, the probability must be larger than if you measure A and B, right, in the parallel directions. So this is a super general inequality, meaning that if any classical local hidden variable theory will satisfy this inequality. And so we can, of course, test this if we have a quantum mechanical entangled state, right? So we can compare the 2 things and see what we get. So with quantum mechanics, if we assume that we have an entangled state now, what ends up happening to these probabilities, if they start to equate to these weird trigonometric functions as a function of theta, which is the angle between these different axes, right? And so how we get these things is kind of this notion again of casting the shadow of one arrow to the next arrow and kind of summing up these things to get these probabilities. And these are little details. But then the question is, if we have these quantum mechanical states for any value of theta, can this inequality be violated, right? So that's the key question, why I put a question mark on the inequality. And the answer is yes. So for all you CU prime students out there, you have done this incredible experiments with your esteemed instructors with pendulums where you do small angle approximations, right? So when you do a small angle approximation, what happens to sine theta is it becomes approximately theta, right? So all these things can be small angle approximated, and if you use that approximation, what we end up getting is that you have theta squared over 4 is supposedly supposed to be larger or equal to theta squared over 2, which is false, right? So we get a violation of the inequality with some value, with a possible value of theta in quantum mechanics. And so provably then, Bell showed that his inequality wouldn't hold if you actually had entangled states. So this was, foundational in the study of quantum mechanics and kind of the establishing of the field at the time. And it's a huge result. All right, so what's the next step then for Bell's inequality? I mean, it's some theoretical result that some theorist in an office or in, I don't know, his room or whatever was thinking about and wrote down on a piece of paper. But how do we actually know if this is true, right? So this is where experiments come into play. And so unfortunately, the way that Bell's theorem is formulated in its kind of initial formulation is very hard to test experimentally, because in actual experiments, when you measure a photon, you basically destroy that photon. There's no way you're gonna send that photon through another polarizer and measure that same photon again. So it's very hard to do these simultaneous measurements of 3 different polarizers. But so here comes in John Clauser in 1969, along with his collaborators, Horn, Shimony, and Holt. Together, I'll refer to them as CHSH. And so they modified Bell's theorem into a more experimentally friendly form, which allowed them to only have to measure each photon once, but then compare the correlations between those photons by counting statistics. So you do some kind of counting, and you define some new measure, which they call S. And this is the new inequality via a classical hidden variable theory. So if you had this new modified Bell CHSH inequality, if you had classically correlated variables. Otherwise, if you assumed a quantum mechanical state, you could actually exceed 2 over here, up to what they call Searlson's bound, which is 2 root 2, which is about 2.8. So if you had a perfect quantum system and you were to run quantum mechanical experiments with entangled photons, you can actually get up to 2.8. And so this allows a way for experimentalists to actually measure a violation of Bell's inequality, Bell CHSH inequality. So here's a little schematic of the experiment that Clauser set out to do with Friedman, his collaborator, in 1972. So essentially what they had is they had a photon source that would send out 2 entangled photons. So you generate 2 entangled photons. They would pass through these polarizers. And if you measured parallel or anti-parallel, they'll get detected by 2 different detectors. And you keep running this experiment and you can build up statistics and then measure kind of these correlations between these particles. And this is exactly what they did. So you can imagine these polarizers as this, like, these sunglasses that I had early on in the GIF. All right. So actually, a fun fact, you can actually buy one of these apparatus that you can put on your tabletop and run the CSH experiment and see a violation of Bell's inequality. If you have, 30,000 euros to spare, you can go to p2s.com and buy one of these cool kits, but it's just something I wanted to mention. It's pretty cool. But so, I mean, this is to say we've come a long way from 1972. All right, so there's one thing though that we've assumed about these experiments. So if you go back to the schematic over here really quickly, there's a few assumptions, and this is true in any general experiment, but also particularly in this experiment. If we really wanted to test if the entangled state really violated Bell's inequality, we have to make sure that our experiments are loophole proof, meaning that there's no possible loopholes around kind of the result that we're seeing in the experiment, right? And so this is where the other Nobel laureates come into play. So we have assumed that each entangled particle doesn't influence each other. So there's no other kind of hidden variable that's happening between the entangled particles. And also the measurement apparatus doesn't kind of have a back action into when you're preparing the entangled photon states. And so this is kind of saying there's no hidden variable. We have to assume there's no hidden variable, that the actual experimental setup itself isn't influencing the results of the experiment, which might seem kind of crazy, but we have to rule it out in some way. And so this is where Alain Aspect and Anton Zeilinger come into play. And so they did 2 loophole suppressed experiments, and I say suppressed instead of loophole free because it's hard to, and putting the particular dates in which they first did their experiments, there's been a lot of incredible advances from there, which I'll talk some about later, but just to get a sense. So it's loophole suppressed in that they can now randomize the process in which you polarize the 2 different photons. So early on, an experiments would come into the lab, they would polarize the polarizers in a particular way, run the experiment, and then count the statistics. But maybe that action of changing the polarizers had some effect on the statistics that you get. And so to prevent this, Alain Aspect first proposed this experiment where he would have an apparatus which would randomly flip the polarizations of these polarizers. And you can't say that, well, this is definitely affecting the experiment because they're kind of randomly switching around. And so the different statistics will give you different results, of course. And this is really cool. I think he had like a 6-meter long channel where he shot a laser and he had to switch his polarizers faster than the time the photon would take from the end of that beam line to the end, so less than 6 meters. And so I think he had to switch these things in like 20 nanoseconds or something, which is mind-blowing. Right, and so this is why it's really Nobel Prize winning science, because of these amazing experiments that you have to build and formulate and think about and do in the lab. Cool. So as I alluded to earlier, that was incredible science by the incredible Nobel laureates that have won. But science still trudges on every day, and we have to keep, looking for more loophole-free experiments. And so there are some actual experiments that have been done in Boulder right here via this huge collaboration, and also some just in Boulder itself, in NIST just down the road. And I'm that way. Thank you. Which is really cool, but I'm going to highlight one of these experiments because I thought it was really cool. So there's this experiment that was done at NIST that was published in Nature Journal, and it's called Challenging Local Realism with Human Choices. And what they did, and this is a quote from the abstract of the paper, which I thought was insane. So they recruited 100,000 human participants to play some online video game. So essentially they made this applet, and these people will play some game, and they generated essentially 97 million binary choices of different polarization possibilities. And so because they don't have any influence on these people, supposedly, so they don't have any influence on these people, all these random choices are basically, random and kind of set by these humans that they have no interaction with. And so there's no bias from the experimental setup and the experimentalists themselves. And all these choices will be sent to 12 different labs around 5 different continents for 13 different experiments. And they would use these different platforms, so not just photons, but also you can entangle things like atoms and superconducting devices, which is really cool. And of course, one of the collaborators was right here in NIST in Boulder. And of course, many other amazing institutes all around the world, which I thought was really cool experiments. Cool. And so just to motivate you a bit more that, Boulder is actually a great place for science. And so you made the right choice in coming here. There are, of course, amazing research facilities and research opportunities right here on the main campus as well. And so, as I mentioned, there's JILA Tower over there where there's a lot of cool research in quantum physics, but also just here in the Green Tower, there's a whole bunch of cool quantum physics research that's happening. And of course, there's amazing Nobel Prize winning science that has been done here as well at CU. So here's a little picture of the four out of 5 of CU's Nobel laureates walking along, where is this, University Avenue? Yeah, right there. Thank you. Yeah, so this, I thought it was a cool picture to just put up, and great science is being done here, and I encourage you to explore these opportunities. Just to mention a few other people who have won some incredible prizes and who are doing some incredible work. So recently, Professor Adam Kaufman, who's also did his PhD at Boulder actually, and so did Ginny over there. But so both of these people have won incredible prizes: New Horizons Prize, the Breakthrough Prize in Physics, for their works in optical tweezers. So optical tweezers is something really cool. I'm sure some of my colleagues are happy to talk to you about these things, but essentially you're literally using lasers to tweeze individual atoms, so you can pick out these individual atoms, and so have really precise fine control of quantum systems and allow them to interact and move them around, which is really insane. And then Ginny does amazing work, experimental work on atomic clocks, where we can measure, what is it now? You can measure time to 10 to the minus 18, 19, 18, one of those numbers of a second. So that's a million billion of a second. You can measure the accuracy of time because of his clocks. And also apart from amazing experiments, they're also great theoretical researchers. So Professor Anna Maria Ray, who's a MacArthur Genius Fellow over there, who does incredible work on electrical systems. And I encourage you, of course, if you're interested in research opportunities, to explore, these groups and also other amazing groups around JILA and Bohn, sorry, and NIST. And then some shameless publicity for my own advisor. So I also do research here at CU under my advisor, Professor John Bohn, who is a theorist, and he does research in atomic and molecular systems. And so here's a whole bunch of research topics that he works on. And the bolder ones are the things that I work on personally. And if you're interested in any of these topics, I'm more than happy to talk to you about it after the talk, or, you can contact Professor Bohn directly as well, and he'd be happy to talk to you. Cool. All right, so let me, in the last kind of couple minutes of the talk about kind of a day in the life of what I do here in graduate school. So as I kind of mentioned from the previous slide, that I do theoretical research in physics. And so I would say that I can probably categorize the things I have to do day to day into three main umbrellas. So the first of which is literature review. So I have to, kind of really broadly survey the research environment and the research climate, that I, to make sure that you're not reinventing the wheel every time you write a new paper, and also to stand on the shoulder of giants, of course. So there's so much incredible science research out there that you should really get familiar with before you jump into a project. And it's really cool and really exciting to read about these things all the time. So the other thing I do is of course, theory investigation. So after reading all these papers and all these fun stuff, I have to actually do some science and generate some novel work for myself. So I, discuss with collaborators and discuss with my advisor about cool science topics, cool science projects that we can work on, and develop theory for those projects. And lastly, I think this last part is also very important that people don't put a lot of emphasis on, is writing and communication, because at the end of the day, science is a big human system, right? And so it consists of humans. And as much as we like to say, well, science is kind of this objective truth and everything is objective, well, it's still, run by humans, and humans still do science. And so one of the things is writing and communicating your research out there and learning about new research via talking to people and collaborating and giving talks like I'm doing right here, is a good way to get science out and also to learn about new science. And so I highly encourage, communication and writing and collaboration in general, as an undergrad or a grad student or wherever you are in your science journey. All right, cool. And so that will sum up my talk. And I hope that all of you go forth and do amazing science.
Thanks, Reuben. Yeah, so we want to hear from you. Do you want to take a minute and fill out this feedback form, the QR code, and there's a link just to tell us how the talk went, and so we can plan for future talks as well. So we have 2 more talks in the semester that we're going to be having, but in the meantime, we have plenty of times for questions for Reuben. Does anybody have any questions?
Yes.
The day in your life thing.
Yeah. Sure.
So for step 2, theory investigation, like, what does it actually look like if I drop by your office while we're investigating?
Oh, that's a good question. It looks nothing like this. I don't do experiments. So I just really wanted to put this picture on the slide. But yeah, so yeah, great question. Thank you. So the question was, I guess, for the Zoom audience too, what does a day in the life of theory investigation actually look like? And I would say it's a mix of 2 things. So one of it is a lot of numerical work where you have to write a lot of code to try and model physical systems, and then use computer technology, the wonderful computer technology that we have, to run simulations to simulate the systems so that we can understand and describe phenomenology that's happening in these systems. And then the other part is a lot of kind of pen and paper theory investigation, I would say, where you do all these algebraic manipulations to try and synthesize theories that are out there, or even formulate new theories that you might be concocting, to better understand and get analytic insight into what's happening in the theoretical world of research that you're doing. Yep. Yes.
So when you were discussing kind of the experiments that you conducted regarding the entire theory founded upon the 2022 Nobel Prize, just seems kind of dated to be 2022. Like why? Like either like why wasn't this awarded earlier, or why did we wait until 2022 to get this award?
Yeah, that is a good question. Probably best for the Swedish Academy of Science to answer. But sorry, so the question for the Zoom audience is, then the work that attributed to the Nobel Prize seems a little dated, and why wasn't the prize awarded earlier, right?
Yeah.
So I think it's a mix of a few things. I mean, again, so one thing is a human system. Sometimes, there's issues, between people, or maybe not really political issues, but you have to make sure that, first of all, the science is legitimate, which takes some time. You also have to make sure that there's no other deserving awards that are out there that should be awarded, because there's, of course, a lot of wonderful science are being done every year, and there's a lot of cool things. And then also, kind of what those Nobel laureates are up to these days, and what kind of work that they're doing, and how they're attributing to the work that they've done so far.
Okay. Thank you.
Sure. Yes.
You say that John Bohn,
Yes.
what kind of stuff did John Bohn do?
All right. So the question was, what kind of stuff does John Bohn do? So we do theory research, and well, I'm hesitating because I don't want to say there's a lot of stuff and then not say anything else. But so, well, maybe I'll talk a bit more about what I do with him. So in particular, we study gases. So these are like, if you have many atoms that are not, solid or liquid, they're in a gas phase, but they're really, really cold. And so a lot of kind of the internal structure of the constituent atoms are not relevant, because they're literally frozen out because it's so cold. So they can't move internally. But what's still interesting is that the gas collectively still has very interesting phenomena that's happening. And what dipolar physics is that because some of these atoms, they interact via dipole-dipole interactions, which are essentially like, you can think of little magnets. Magnets are dipoles, and they kind of bump into each other like magnets would. So these like atoms that are floating around, and they're little magnets, and they're bumping into each other. And actually, the emergent phenomena that happens from these bouncing magnets can be very interesting and very insightful to study theoretically.
You said that we should
Yep. So machine learning is a broad term, of course, for any kind of data-driven algorithm that you can use to gather information about a quantum system. And so another way to say this is, how much about a quantum system can I infer if I can probe the quantum system in a particular way? So let's say I have some quantum system that I don't know how to characterize in a lab or in an experiment, but I can only measure a small portion of that quantum system, and I can watch that small part of the quantum system evolve in time. And so that gives me a lot of data, right? So I can keep doing this, I can keep probing the system, and I get a lot of data. Can I use all that data to then teach me something about that quantum system, or infer something about that quantum system? So that's kind of the idea of what we're trying to get at on that project. Yep.
So are you
Sorry, I
sat down the
oh, right now it's done internally at the moment. Yeah. Oh, yes.
earlier you're talking about how we're producing two entangled states from the photons.
Yeah.
Or how, it's like the basic way of producing an entangled state. How do you actually generate something that you know is
Yeah, that's a good question. So the question is, how do you actually generate entangled photons, right? So the most I can say about that is just words and jargon. And I think it's best if I left this answer to an actual experimentalist who knows what they're talking about. Like my friend over there, Peter, behind, you can probably ask him about it. Or maybe you can answer right now.
One way I know about it is you have nonlinear crystals where you shine light and if the power is high enough, you'll just generate carried photons. And blah, 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 the photons are okay.
So let me just repeat that. So what Peter said was, in a lab, you can shoot a laser at what they call a nonlinear crystal, and it will generate automatically from that interaction of the laser and the crystal itself, generate two photons that are intrinsically entangled and correlated in that way. Yes.
Is there entanglement based on just like a conservation of how do you know how to describe it? Just like polarity? Like, is that how it works? 'Cause they're opposite to each other.
Yeah, that's a great question. So the question was, is there entanglement generated from some conserved quantity in your system? Yeah, so a lot of entanglement, so a lot of systems that are actually two levels, people like to think of them in terms of some form of spin. And so the spin is kind of this quantized version of angular momentum in quantum mechanics. And a lot of the times you can exploit the conservation of angular momentum to get generate a entangled state in your system by some cool process. Yeah. Yeah. Yes.
Another standard way of doing it is there are these types of states that also have some notion of being perpendicular, and you interpret them on a B square. And that will generate an entangled state in the outputs of the B square. So it's like mixing it on this B square that mixes the B.
Oh, that's cool. Okay, so yeah, Jacob was commenting on another way to generate entangled photons is if you, and I think you send two polarized photons to each other.
I think I have two squeeze states that are squeezed along different axes, which is why I said it's not perpendicular.
Okay, so
Perpendicular, like.
yeah. So there are two states that would normally be, well, I don't know any other way to, well, they're squeeze states. It's the word. Yeah. But so they're a special type of light that's prepared in a very particular way that are not entangled initially, but you send them together and then they interact and then they come out as entangled. I think that's the point.
Well, if you guys have any more questions, you feel free to stick around for a few more minutes.
Yep.
You can come up to the front. If not, let's thank Reuben one more time.